Swayam Prabha. Digital India. Educated India.
Let's start. Welcome to Introduction to Electronics course. Today, we have been discussing C amplifier circuit. For example, we have discussed very simple common emitter amplifier where we applied Vin at the base. VCC is basically the supply voltage, okay, and Vout is the output voltage we are measuring at the collector, okay. And these circuits acts as an amplifier circuit, and we found we have learned how to draw the small signal model. This was R pi, this was GMV pi, and emitter is grounded, and there is RC resistance, which is again AC grounded through that DC VCC voltage, right? So this was the small signal circuit of this common emitter amplifier, and we have found out these relations V out versus V out over V in, that is basically the gain, which is GM over GM multiplied by RC, okay. We have also learned RE. You remember we showed that how to calculate RE in this kind of circuit, where R to be R pi and R naught R out comes out to be RC, okay. These things we have discussed in the last class, and it is possible to show that AV is minus beta R out by R in, right? So if we know R out and R in, we will be able to find out the gain of the circuit, okay. Now if we consider that the VA is not VA is less than infinity, that is there is a finite R naught, small R naught, so R naught comes out here basically, okay. Then this gain will change a bit, okay, because then the gain will be RC parallel R naught, okay, and the corresponding output resistance will also change, okay, right, but Rin will remain the same, okay. So again, this part also we have discussed in the last class. Now if we I think we have also discussed the second case, say case 2, where we have assumed that there is a emitter is degenerate, okay. That means there is a resistor between emitter and ground, and I can't remember we finished the calculation of this particular circuit, but let me just go through it once more. In this circuit, you see, if you increase the input voltage by delta V, okay, then then this whole delta V will not be across VBE, right? Some part will be the small part will be across this base emitter voltage, okay, and rest of the things will be across R across RE, okay. So if you have like so in other words, RE is absorbing some part of that in input signal change across it, okay. So if RE is equal to 0, if RE is equal to 0, that is if it is not a degenerate case, then we can basically that change in delta V at the input signal, we will change the current, will change the collector current uh, GM delta V, right? Because you remember GM is delta IC over delta VBE. That's basically GM, right? Transconductance. So we can write IC is equal to GM delta V, and corresponding change in IB can be written as this divided by beta. What about when RE not equal to 0? That is, we have connected a finite resistance between emitter and ground. In that case, IC will be less than IC will not be equal to GM delta V. You see, because some part of delta V is absorbed by RE, and correspondingly IB will be less than change in base current will be less than that of what we have when we don't use RE, okay, when we short the emitter and ground. So change in IB will also be less. So this implies that if we look at RIN from the base side, okay, RIN will be larger, or RWin will increase, because you see that change in IB is less. So that's intuitively we can say that RIN, if we look from the base side, will increase. Okay, how much the value of RIN? Well, we can write it here. We will so RIN will be basically we will see how RIN will be this value. Okay, we will see later on. But RIN will not be R pi plus RE. Okay, it will be R pi plus, there is a multiplication factor beta plus 1 into RE. Okay, that is how we are getting that equation. We will discuss that. Okay, now we can find out the gain of this circuit. Okay, in the same fashion we calculated when we have when we don't have RE. Okay, so again this is my R pi, this is my GM V pi. Okay, and this is RE, and this is your RC. Again, I am not considering small R naught. Okay, that is the output, that is that resistance comes because of the early effect. I am not considering that for the time being, and you can calculate the gain by basically just in the same fashion. Okay, so V out over RC is equal to GM V pi. Okay, minus sign will be there, and we can write VRE. Let me go to the next slide. Okay, yeah. So VRE we can write equal to, so VRE, you see there are two currents. Okay, you see there are two currents. One is current from this side, and the another current is from this side. Okay, so if you calculate VRE, it will be V pi R pi, V pi over R pi plus GM V pi multiplied by Re. Okay, and you see you see uh, you see V in is divided into two parts. The voltage V in, one part is V pi and another part is divided, another part is across Re. Okay, so we can write that V in, because all we have to do, we have to relate V in and V out. V in we can write V pi plus plus VRE. Okay, that is the voltage drop across, so we can write V pi plus this. Okay, and then ultimately you can we can have this V out over V in, where V pi is basically you can find out V out over V in is equal to, I think I can't remember, I think we have ended the class with this equation, right, in the last class. Sorry. So this is the ultimate equation, and you can of course you can write Gm much greater than 1 by R pi, and if you consider that, you will ultimately get AV, that is the gain, is equal to GMRC over, of course there is a negative sign. Okay, you will have 1 plus GMRE. Okay, now if you divide both numerator and denominator with GM, you can simplify it a little bit further. Then you will have RC 1 by GM plus 1 by plus RE. One important thing I think I mentioned at the end of the last class, if you see this equation, you see this gain is basically resistance at the collector, okay, divided by resistance divided by the resistance you see from the emitter side, that is 1 by GM. You remember 1 by GM is the resistance. If you see a if you see from this side, that is basically 1 by GM, remember. Okay, so so this 1 by GM plus the resistance you connected to the emitter, so placed in series with emitter. So you remember this point, that gain is basically if you look resistance from the collector side, that is RC, or resistance connected at collector RC over 1 plus GM plus RE. Okay, now now there there is some interesting interesting example given in Rajavi's book. I think I should include that in our discussion. Say for example, if I have two transistors, okay, connected like this, okay, then what will be the gain? Okay, without going into the detail of drawing the second stage and also the first stage and all that, the small signal models, you can straight away simplify this circuit if you use the concept we have developed in last few classes. You see, this is basically, if this transistor is Q1 and this transistor is Q2, you see the input resistance is as this emitter is input resistance of this Q2, then this input resistance is R pi 2, right? If you look from here, so you can simplify this circuit in a much better way. Okay, so you can straight away write the gain is equal to resistor connected at the collector over 1 by Gm1, that is the transconductance of the transistor 1, okay, plus Re parallel R by 2, you see. So you can simplify quickly, because we have learned that from the base side, if you look at the input resistance is R pi, okay, if this is emitter is grounded, that is the case with Q2, right? What about if we change the position of base of Q2 to the collector terminal, okay? In the book there is another example which is which I again would like to discuss. So instead of connecting it to the emitter, if we connect, so this is your V out, sorry, should have, okay, and this is VCC and RC. However, I have connected so this is my VCC, okay. So this time the base is connected to the collector, okay. So this is Q2 and this is Q1. So again we can replace this Q2 because it is basically R pi 2, okay. In that case we can basically simplify this circuit okay. We can simplify that circuit by connecting R2 to the collector, and for a small signal model, this RC and R pi 2, you see they are in parallel, because you are basically grounding this capital VCC, because that's the DC voltage, right? So again you can very easily found out the gain of the of this circuit, which will be RC parallel R pi 2 at the numerator, and denominator will be 1 by Gm1 plus Re, okay. So it's very easy and intuitively you can guess if you remember the concepts we have developed in the class, okay. You don't have to go through all the calculations and put the second transistor and all that, okay. Now so let's find out the let's go to the next slide and try to find out the input resistance. You remember we directly wrote the input resistance of this of our emitter degenerated amplifier circuit, okay. Let's calculate how this is coming as R pi plus 1 beta plus 1 Re. That's the input resistance, right? From here, if you look from here, Rin, we can find that out, okay. So if you replace you remember to find out input resistance, what you have to do, you have to connect a test voltage at the input, okay. That will give you a test current. All we have to do is to find out test voltage over test current, okay. And this is your R pi, this is Gm V pi, okay. This is your Re, and there is RC at the output, and we are neglecting the R naught, that is the resistance because of the RD voltage. Okay, we are neglecting that for the time being. So what we are doing, we are calculating the input resistance of the circuit. Okay, and you can do that since V pi is equal to V pi is equal to R pi Ix. Okay, R pi Ix, so you can write the current through current through the RE circuit. Okay, that will be the this current Ix plus GM V pi, right? Now, right, we have just mentioned that. So this is your GM V pi, that's the current, that is Ix plus GM R pi into Ix. Okay, and so this is the current I am writing through RE. Okay, current through RE. So this is GM R pi is beta. Okay, so Ix 1 plus beta, right? So you can basically write Vx equal to R pi Ix plus Re 1 plus beta into Ix, right? So you see your Rin is coming out to be so this is an important relation to remember, that in the C amplifier circuit, the input resistance Rin, the input resistance Rin will be equal to R pi plus 1 plus beta into Re. So the resistance you will connect at the emitter, you have to multiply with beta plus 1. Okay, and then add to the R pi to get the input resistance. So the good thing is, this circuit not only stabilize your bias but also increase the input resistance of the amplifier. Okay, and this increase in input resistance is you have to just multiply with beta plus 1 with that resistance, then you get that increment. Okay, so the point to be noted here, it is not because I have seen many papers, they have many exam papers, the student make mistake. So Rin not equal to R pi plus Re. You see here Rin not equal to R pi plus Re. Here it is R pi plus beta plus 1 Re. Okay, so there is this multiplication factor, simply because the same current is not flowing through R pi and Re. Okay, the currents are different, right? So you have to keep in mind that. So if I just draw what I try to mention effectively, so this is not only Re. It is basically if you try to pass same current through it, you have to take it as like 1 plus beta Re. Okay, because the same current is not flowing. You see. Anyway, so what about R out? So Rin we have found out of this circuit. What about R out? R out is simply equal to RC. You see, because in case of R out, you remember we short this input terminal. Okay, we short this input terminal, and if we short this input terminal, that will basically zero this zero this current source, right? So you will end up with okay, if you short this input, then your V pi will be 0. Okay, and also that makes this current source is also 0. So in that case there is no effect of RE being connected to the emitter as far as the output resistance is concerned. So R out we can straight away write equal to RC. Okay, R out we can straight away write equal to RC, right? So this is I thought that I just discuss one important point to be noted, as the gain is you see the gain of such circuit is RC over uh, sorry, uh, uh, so let me go back. Let me go back once more. So what I try to mention here, we have mentioned it already. So this RE, the purpose of RE is, let me repeat it once more. The purpose of RE is it is stabilize the biasing. Okay, first. Second is by negative feedback. This is we have mentioned long ago. Okay, and other point is this RE improves RE. Okay, and doesn't have effect on R out, right? Now this however, what this RE does, RE reduces the gain. You see, RE reduces the gain. If you see, so original gain was GMRC minus GMRC. Because of this inclusion of this RE, the gain reduces. The voltage gain of this circuit reduces by this factor, right? So what we can do, we can, yes, yes. Is there anyone have any queries? Okay. So so the gain will reduce because of inclusion of RE. Okay, so you will see in the book also we can bypass this resistor. Okay, so a part or full of this resistor depending on your requirement. So you choose a capacitor in such a way, in such value, this capacitor is known as bypass capacitor. Okay, that AC signal will not see this RE. Okay, sometime you will see this whole RE is bypassed. Sometime you will see a part of RE is bypassed. Okay, the whole reason is okay, sometime you will see a part of the RE is bypassed. Okay, if you bypass the whole RE, you choose a capacitor in such a way that the AC signal will see this capacitor as short. Okay, you see impedance of the capacitor is 1 by omega. So if you choose the capacitor value in such a way that AC signal see it as a short circuit, so the AC signal will go through this path. Okay, so in that case you will have gain equal to the gain as if the resistor is not there. Okay, so in that case this resistor will basically stabilize the biasing but will not have effect as far as the input resistance is concerned. However, you bypass it partially, then this RE1 will take part in improving the input resistance, whereas we have partially bypass it, so it will not reduce the gain as much as the if we keep the whole RE1 and RE2. I hope you understand what I am saying. Okay, so this is the way we deal if we want to improve the gain. Another point is I
Sir,
forgot to, yes, please go ahead.
sir, if you are introducing a capacitor,
Yes.
then won't the expression for input resistance or input impedance would change?
Because we choose the capacitor value very large and such that this capacitor will act as a short. Okay, I mean you can take this to calculate when you find out the input impedance, you can take this on board, but the capacitor value is purposefully chosen in such a way that the AC will see it as a short. Okay. So this 1 by omega c will be very large and the AC will see it as a short, so it will be basically a short circuit for the AC signal. For the DC signal, the capacitor will act as an open circuit, and so RE will be there for the biasing. Okay, so you
So
don't have
C
to
will
consider you don't have to consider, if you choose capacitor value properly, then you don't have to consider this capacitor for calculating the input or output impedance. Okay. Now we can simplify this gain formula a bit more. I should have told you before. Uh, 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 if your GMRE much greater than 1, we will have this you see, so that is not when we that is not when we are applying any capacitor. This is just a degenerate emitter degenerate circuit where we haven't used any capacitor. Our gain formula is this, right? Minus GMRC over 1 plus GMRE. So we can simplify it as minus RC by RE if GMRE is much greater than 1. What this tells us is if we choose in RE properly, then the gain is will be independent of transconductance of the transistor. Okay, gain will simply be RC over RE with a negative sign. Okay. So that is, I thought, an important point to mention. Now there is another thing I would like to discuss. One particular example which I think worth mentioning. Yeah. So say I have a certain, okay, so this say this is one circuit. Okay, and you can find out the gain of this circuit. Say example 3. Okay, this look bit complicated, but if you think carefully, this is very easy. Where this DC current, we have sorry. Yes, please go ahead. Okay, so this DC current is basically we open circuit for the small signal model okay, and this DC voltage will short circuit, right? So we can redraw this circuit, and right, because you see through this, if the capacitor value is large, through this capacitor, this R2 is basically shorted to ground, and R1 is also going to the ground. So you see RC and R1 is parallel, and R2 is effectively a emitter degenerate configuration, right? So you can straight away write the gain where your RC parallel to R1, okay, and this will be 1 by GM plus R2, right? And corresponding Rin that we have come across already, 1 plus beta R2, and R out will be equal to RC parallel R1, okay. I hope this is clear to you. Now uh, now so far whatever we have considered that this is a very simple common emitter amplifier circuit, and we are trying to find out gain of that circuit. Now next thing I would like to discuss is if we have a resistor in series with this Vin, okay, that will be the case in reality. You see that Vin will have internal resistance associated with it, okay. So if that is the case, then your calculation is a little bit different, and we will see in a minute how that changes your gain or your input resistance, your output resistance, and all that, okay. So what we are considering now, that I have the same circuit, or the only difference is now I have a resistance in series with this input signal, which will in reality will be the case. We haven't considered that before because we have much more simplified version of that common emitter discussion. So if we assume that Vin has a resistance RB, then you see the gain will drop. The reason the gain will drop simply because a part of Vin will be drop across this resistance RB, okay. So Vin will drop across RB, Vin will drop across VB, and also will drop across RE, that is basically effectively beta plus 1 RE, right? You remember? This is basically effectively beta plus 1 RE, right? So Vin will basically drop now this with this additional resistor RB. So if I assume this is a point A, so we know the gain. We already found out the gain if there is no RB, right? We have found, so this is voltage at A. So we already found out the gain of that common emitter amplifier circuit if RB is not there. But if RB is there, some part of the signal will be dropped in across RB, okay. So we can again, this is very easy. If you think carefully, you will be able to find it out. Okay, so this part is already known to us, right? All we have to do, we have to find out VA over Vin. This VA over Vin is just a voltage divider circuit, and we can straight away write Okay, so that is VA over V in. And what about so this is VA over V in. What about V out over VA? That again we already know. Okay, right. So if you use those two will
So,
yeah,
so can you go back to the previous slide?
yes, of course. So we are doing that, we are basically finding out VA over V in. That is basically the it is basically a resistor divider. Okay, voltage divider. So you we uh, right, R pi
Thank you, sir.
beta plus 1 RE over this, and this is what we already know. So
Sir,
yeah,
sir, just previous page.
yes.
Sir, when you are placing an extra resistance RB, you are reducing the gain, right?
Yes.
So then what is the use of doing that? Because we want the
No,
gain to be
I
highest.
am not intentionally adding that. Actually, what happens whenever you will connect a source which you want to amplify, the source will have internal resistance associated with it. Okay, so that internal resistance will. You remember we were discussing. We were at the beginning of the amplifier. We were discussing micro. We were discussing microphone. Okay, and in the microphone example, you see you have a internal resistance associated with that microphone. So any signal you want to amplify, there is a resistance, internal resistance associated with it. Okay, so in reality this will be there even if we it deteriorates the gain. Okay, so we will see how much that deterioration, right? So we come this.
Okay, sir.
Yeah, so so basically this is R pi plus beta plus 1 RE plus RB multiplied by you can if you carefully check that check the okay previous slide. If you check that, you can you just multiply this R pi, you will have GM R pi on top. In the numerator you will have GM R pi RC, that is basically beta RC, right? And this term you can write in the form of beta, and you will have this, right? So you can basically this and this will cancel out. Okay, and you will end up with beta RC okay. Now you can simplify it a bit more if you divide the whole thing with beta or say beta plus 1. Okay, beta plus 1 is the same thing here. We can approximate that, and you will end up with so you see again we have come back to that expression where this is the gain we got when we don't have you see when we don't have RB. Okay, and when we include RB, the effect is it is that additional term, but RB is we have to divide RB with beta plus 1. Okay, so it will be easier to remember if you simplify the expression this way. So this part is without RB. We got that expression, and because of the RB in the denominator you have that term. Okay, uh, what about the input resistance? Input resistance.
Sir,
Yes.
so you divided beta.
Yeah, but just for the simplicity, I have done that. I mean, you divided by beta or beta plus 1. It's divided by beta. Here I have done. You are right. But the reason I just change here to get that expression, you see. So beta is maybe 200. So 200 plus 1, 201 is the same thing, I am assuming here. Okay. So just to simplify the expression so that you see that this is the gain of that circuit when there is no RB. Okay. Yeah, I hope you appreciate. Otherwise, we will not get that exact expression. But if you put RC, RE, RB, GM, you will get the almost the same gain if you choose beta or beta plus 1. Okay. So to get that, they get this nice simple expression which is like analogous to that when there is no RB. I had to divide the some part as like beta, this and this I have divided with beta, and this part like beta plus 1. Okay. Anyway, I hope you can appreciate that. So the whole thing, the point I would like to mention is, if you just remember the gain with where RB is not there and RB is there, there is only this term, this additional term at the denominator. Okay. What about the what about the gain of the what about the input what about the input impedance of this circuit? Okay, input impedance of this circuit again can be easily found out. Okay, because we have already done the calculation. Okay, so you see, this is say R in 1, this is say R in 2. Okay, this is your RB. So R in 1 we already know, R pi plus 1 plus beta RE, that is R in 1, and of course then R in 2, which is the complete input impedance of that circuit, will be beta plus 1 RE. Okay, so your input impedance will be a little bit higher because of the RB. Okay, and of course your output impedance will be same as RC. Okay, of course we are not considering R naught here, right? So here we will stop the class today. In the next class, what I will do, I will consider the biasing. I haven't considered the biasing yet, right? So we will add single resistor biasing and voltage divider biasing, and we'll see how those changes the gain. Okay, because ultimately you need to have biasing and the AC signal which you want to amplify, because biasing will ensure your Q point that we have mentioned already. But so far in our calculation we haven't considered those resistors, right? R1, R2 and all that, Thevenin voltage, Thevenin resistance and all that we haven't considered. So in the next class we will consider that, and we'll find out the gain again, and we will see whether the gain is changes because of those single resistor biasing or voltage divider biasing and all that. We will consider those things. Okay, so with this I am closing the class today. If you have any doubt, please raise your hand.